Good afternoon, everyone. I'm Brian Ptterson, Chairman and co-founder of the eMerge Alliance. My presentation this afternoon is about mesh network microgrids. Due to the virtual format of my talk, no refreshments will be served, although I will endeavor to satisfy your thirst for knowledge and information. So let's get going. Now, we've been blessed with the largest machine man has ever made, the electric grid, which has, for the most part, met customers' demands in real time, every second of every day for the better part of a century. But that's just it. Customer demands, which hadn't changed much in 100 years, are rapidly changing now. Much of that change is resulting from two major contributing factors: the way we are choosing to generate electricity and the way we use it. So keeping that big old machine going for another 100 years is going to take a little more than a fresh can of oil and a few spare parts. And yes, we can't do without it. Simply put, electricity underwrites the economy of the 21st century. Without a stable electricity supply, health and welfare are threatened, and the U.S. economy cannot function. But when a power system fails to deliver, clean energy or not, the consequences can be catastrophic. This is truer today than ever before, given our increasing dependence for almost all that we do on the supply of energy, and particularly in its most useful form, electricity. So today's subject is not worth talking about until we understand the problem we are trying to solve with mesh network microgrids. The increasing vulnerability of our electric power system, with its disabling faults and interruptions in service, are just not acceptable anymore. Summarizing what's described in detail in the Smart Electric Power Alliance's microgrid playbook would simply be to say, things aren't getting any easier or smoother on the road to safe, clean, high quality, uninterrupted, and abundant electricity. You may even be able to add a few of your own events to this growing list. Some of them short duration, like downed utility lines from a traffic accident, or the failure of a piece of equipment in the transmission or distribution infrastructure. All of these can cause local blackouts that can be disruptive and very costly. So let's face the reality. Electricity is critical to the sustainability of our civilization in its current form. Suffice it to say, a few days without electricity can be very disconcerting and even threatening. But a week, a month, or a year without electricity, I think we all shudder to think. But let's take a broader view and explore some of the more positive and obvious inevitabilities in our situation here. Both the building and power industries are kind of long overdue for some changes. We are starting to see our buildings becoming electroactive and becoming more and more a part of the solution and not the problem. Our built environments are getting more resourceful and efficient with electricity. Our information and energy systems are going from being someone else's problem to being an integrated part of our life, leaning in the direction of personal energy independence. And we're starting to make better use of fuel supplies by moving our transportation propulsion means to electric, even though that will mean we need to produce as much as 30 or 40% more electricity to replace our use of gasoline and diesel fuel in those same vehicles. But while we may be just in the middle of the information age, we're surely at the beginning of a new energy age, maybe even what we might call a new electricity age, based on the electrification of just about everything. And while good information is always a guide, without energy, it's nearly worthless. It's electricity that gives us the ability to do work, or to act, or to create new value. Given all this, what should our goal set look like when it comes to resiliency? Reduce vulnerability, maintain service to critical infrastructure, prepare for large-scale disruptive events, and share the responsibility for resiliency. It's a tough and demanding list. When I think about tough problem solving, I first like to see if the problem has been addressed or solved in a similar but different situation. In thinking about system resiliency, there are lots of success stories and some failures. But in the case of the power system, the nearest candidate is something most of us know a fair amount about: the internet. This is despite the fact that, ironically, one of its biggest vulnerabilities is the potential loss of power to it. The evolution of distributed information systems has greatly outpaced the evolution of distributed electric power systems. On the left, we've gone from the invention of the transistor to the wide use of personal information devices in about 30 years. Yet, even though the invention of the solar cell lagged the transistor by less than 10 years, a similar and even strikingly similar evolution in distributed power has taken over 70 years. Well, if nothing else, we can learn from this history and project it forward. As we've seen distributed information devices evolve to a global network, creating enormous new value in society, so too can we comfortably predict an almost identical future for distributed electricity systems, with a commensurate enormous increase in new value creation potential. When it came to the transformation of the information industry, the tremendous convergence of influencing technologies provided the catalyst for faster adoption, especially when multiplied by the network effect. Look at the list of technologies that are all converging now in the power industry, and why shouldn't we be considering networking to accelerate their progression, lower the cost of systems, and multiply their ability to create value? Well, let's quickly jump through what else we can learn from our 40-year internet experience. First, we see the internet largely depends on a massively distributed capability. Today, nearly 70% of all information, a lot of it video, is created and used locally at the fringe. And whether you're a third grader who sheltered in place at home while attending a virtual math class run by a teacher on the other side of town, or the president of the third largest country on earth who is tweeting 280-character messages to an anxious citizenry, you both have essentially equal access 24/7 from any place in the world. The internet has a hybrid mesh network topology where all nodes cooperate to distribute data to, from, and between each other. The internet can automatically manage flow, self-organize, and avoid faulted or offline routes. The internet has a rigid set of rules for transferring data and a simple standardization of data form. And finally, the internet's operation is based on the premise of holonic transactive cooperation, what I'd like to call the enlightened self-interest of all of the agents, nodes, users, devices, or whatever else you want to call them. And let me see if I can break this down in a simpler way. Holonic, self-reliant units that can act as the whole or as a part of a system. Transactive, capable of acting by trading or exchanging, and in this case, electricity. And finally, cooperation, helpful by doing what is wanted or asked for when possible or necessary. So here's what it might look like, moving from the centrally fed serially connectivity of our 100-year-old power grid to the mesh network connectivity of a grid of grids in layers. To summarize, this grid of grids will first recognize and promote adding new power capacity at its edge. It'll better accommodate natively electronic loads, storage, and generation. And it will enable non-synchronous operation. It will employ the benefits of a mesh topology. It will rely on holonic control architecture, and ultimately enable energy as a service for value creation. Well, so far I've tried to make our case for a transformation of the traditional electrical system to move away from a central station configuration to a distributed generation one. The question is, are we right? Look over the diagram on the left there and find where we are right now and ask yourself, which future is most likely? Centralized, distributed, or hybrid? And as a second thought, based on your view, will the system stay AC? Will it move to DC? Or will it become a hybrid? And think in the 20 to 30 year kind of time frame. Most of us at eMerge have great confidence in our predictions, even though we come at our predictions from quite different directions. That's because in trying to predict the future, we simply focus our attention and give a keen eye on the inevitable. But as a futurist, I still like to keep at least a few toes squarely placed in the present. So let's explore what's going on in the market and see if all of what I have said is and what I've been talking about makes any sense. Probably the best embodiment of what we are predicting is being demonstrated in a relatively new platform offering from a company called Emera Technologies. Emera is a subsidiary of Emera Inc., a utility with $34 billion in assets and operations in Canada, the US, and the Caribbean. Because of time limits here, I won't be able to describe all of the details of their platform, but let me hit its major attributes, and if you want, you can contact them for the rest of the details. The platform is comprised of at least 4 tiers of grid connectivity. Starting at a premise, the first tier is a self-contained box that houses the core of a nanogrid. It connects to whatever power sources are available on site, as well as makes a redundant loop connection to the next tier and the local neighborhood on a peer-to-peer basis. The second tier is comprised of a completely peer-to-peer connected group of similar nanogrids. That is again connected to a redundant loop to a common resource community microgrid. This third tier is typically comprised of locally shared resources and also maintains the connection with the local utility grid. Note that the connectivity between all tiers is direct current, eliminating the complexity of synchronization, frequency, and phase control, and the connectivity of natively DC elements like PV and batteries is simplified. And while the bidirectional inverters are used at the connection points to the utility grid and a traditional AC wired premise, both ends have the option of being DC connected, in essence, giving them an advanced level of future-proofing, should either of these move in whole or in part to DC in the future. There's a lot more detail to it, but there you have it, an early implementation of a grid of grids, perhaps the beginning of an internet. Neighborhood and communities can be further connected into area grids with both AC and DC interconnection. And utilizing higher voltage DC, they need not be contiguous. This allows for a progression of the new technology to be easily evolved over time. The utility can maintain its traditional operations and controls of the existing grid, while the distributed grids manage their transformed portion almost on their own. But these are just diagrams. Let's look at the installed system in Albuquerque, New Mexico. Home to the Kirtland Air Force Base and the U.S. Department of Energy's Sandia Labs, what better proving grounds for this latest of microgrid networking technologies? From this drone's eye view, you can see the basic elements of the Emera grid of grids. You see the residential and local commercial building neighborhood cluster of self-reliant DC connected nanogrids. And I believe they're numbered here N1 through N10. The community microgrid, labeled here as C1, is a large PV, contains a large PV array, which, by the way, is part of the Sandia Labs testing field there. a natural gas generator, and a community level battery stack. And of course, it has the connection to the utility grid, which you see to the far right there. And there is a special lab. If you go all the way to the left, there's a special lab connection that allows variable load testing under varying conditions of the grid itself, courtesy of, again, the Sandia National Labs on that site. Here's one of the NanoGrid supported commercial buildings with both AC and DC charging. The building was purposely wired with AC, but will gradually move its loads to DC over time, just to model out the transformation process. Here's the core of the community microgrid housed in this nice, small, compact outdoor housing. Here's one of the 7 residential buildings. Note the solar panels on the roof, and you see one traditional AC air conditioner, AC air conditioner hanging out of the window there. Here's a shot of the community PV that's tied in at that 3rd level tier. Again, this is part of the Sandia testing lab here. So you see a lot more apparatus than you would normally see in a PV array like this, but it's also doubling as a test bed. Here's one of the myriad of dashboards for the system. This one is a relatively simple one of the whole system. But let me point out a few of its features. The graphic user interface, or GUI, is internet accessible, but can be isolated for security reasons when necessary. And it shows subpanels for the nanogrids, and you see them again labeled 1 through 10. You see community solar, and that's right in this area here, where it's you see just to the bottom right. The community battery, so a little bit further up next to the Amera logo there. You see community generator, and I see the dials at 0, which means it's on standby, as it probably should be. And by the way, this is an active recording of an active period of the actual display. So you're looking at real information as it's depicted in the dashboard. Then you see over again on the right, below the logos there, you see the grid connected inverter, and ultimately you see a representation of the utility grid. Now each of these blocks on the interface have lots of information, and of course there's ways to harvest that information in a variety of ways. But let me just show you one other screen. This one's a different view, simplified neighborhood dashboard. You see a similar individual home dashboard right here in the middle, just about, with the percent solar at 129. You see there's also a view of the neighborhood there. It's all the way over to the far left, and a view of the power flows all the way to the right there. Those little dots that are moving along on the representative power lines. And you can toggle this. It's actually showing real flows of power here, based in terms of amount and velocity. But you can also toggle it over to historical data for troubleshooting or reference, or checking back to see what may have happened if there was an incident. You can see it's all color-coded, and in case you haven't noticed, that's a little bit hard to do with electrons because they're not so cooperative, but just kidding. So in this case, you can see the PV generation flows. The PV is coming off the rooftops there in those yellow or orangish dots. You can also see the nanogrid service flows. That's the blue dots going into the buildings. So that would be AC power going in after it's inverted at the nanogrid boxes out there. And you see the grid bus, which is that mesh, hybrid mesh bus-like topology, where the green dots are moving and ultimately going down to the community microgrid. And if there's excess power, as I think there is right now, or at least it's showing that there's excess power in the neighborhood, that it would be inverted and put back on the grid. Although it may look like a video game, this is the real thing. It shows everything in real time. Although in this case, you're seeing a recording of it. We did make the recording by just literally recording real-time dashboard. What I've shown you is the original pilot of the project, which was completed and put into operation last year. It services live occupied buildings and an operating space on the Air Force Base. And despite the fact that Emera's engineers have continued to do stress testing of the grid using the load bank over at the Sandia lab there in that, I think it was N9 nanogrid. The grid has performed flawlessly for almost a year now. Work is currently underway at this location on 3 more non-contiguous neighborhoods. Each will follow the same basic configuration and will be ultimately interconnected by a higher voltage DC bus and will have redundant connections to the utility for further assurance of resiliency. Meanwhile, several other residential development projects in Mexico and Florida, in New Mexico and Florida, are underway using this approach, lest you thought it was just for the military base or for testing purposes. They will all have a similar modular approach with a kind of a plug-and-play capability of nanogrids. And here's one example, a rendering of a community that will be powered this way in Mesa del Sol, home of several other interesting microgrids. Notice that the buildings don't all have the same solar exposure. And this is where the networking really comes into play. The same is true for the batteries. They're a shared resource, which makes each battery install more economical and right-sized with the community microgrid backing up any issues at the nanogrid level. According to the developers, they think this will be a truly resilient, efficient, and environmentally responsible community. And oh, by the way, for you architects out there that I also mentioned, it looks cool, it looks good. Place a lot of us would love to live. But Emera isn't the only one to recognize the advantages of this grid of grid concept. Others are moving in the same direction. The 3 fundamental themes that unite these efforts are mesh networking, which is allowing the virtual configuration of sourcing, storage, and loads, DC coupling and busing, which is simplifying the interconnect by making it asynchronous and a better native match of power form to sources and loads and their eventual potential move to digital form. And finally, distributed intelligent controls, where each unit can be autonomous and self-reliant when necessary, but operate in a self-enlightened cooperative way with the whole community when possible. And if you doubt the eventuality of a global grid of grids, check this one out. While it may sound crazy insane, Australia will soon start exporting sunshine power, solar generated electricity, to Asia via a 3,800 kilometer cable, affectionately called the Sun Cable. And this is from a country that is the world's 3rd largest fossil fuel exporter. The Sun Cable project initially involves a 10 gigawatt capacity solar farm with about 22 gigawatt hours of battery storage. So global grid of grids, bring it on. Unfortunately, that's all the time we have for today, but I'd like to conclude by saying that the eMERGE Alliance continues to work towards completing new Vanguard power standards to achieve net zero energy buildings and campuses in a highly resilient neighborhood and community microgrid format. The rest of the portfolio of standards work at eMERGE includes residential nanogrids, commercial industrial nanogrids, information and telecommunications, ICT technology nanogrids, AV charging infrastructure, indoor agriculture nanogrids, DC metering, that's revenue grade metering, and dual input AC-DC power supplies. The eMERGE Alliance is a nonprofit open industry association containing commercial, government, and academic member organizations who are developing standards leading to the rapid adoption of hybrid AC-DC microgrids in commercial and industrial and residential buildings, neighborhoods, and communities. eMERGE standards integrate the buildings and campus infrastructure's power and controls and devices in the microgrid platforms to facilitate the hybrid use of both AC and DC power. The standards facilitate greater energy resiliency and sustainability while maximizing the potential use of distributed clean and renewable local energy. And you can learn more about us at www.emergealliance.org, or for direct support, send us a note at help@emergealliance.org. The eMERGE participates throughout the year in SPI, ESI conferences and events, including North American Smart Energy Week, this one, the largest event in North America, where we have been facilitating the demonstration of live microgrids that have provided power to previous face-to-face shows. In this year's virtual event, eMERGE is proud to co-host the Smart Energy Microgrid track in the program. Thank you again, and I hope to see you tomorrow at 3 p.m. for more exciting information about the grid of grids.